In today's video, we'll be talking about electric potential. After watching this video, you should be able to understand the difference between electric potential and electric potential energy, and then understand what a volt measures. Okay, so let's get right into it. Before we start talking about electric potential, I think it's a good idea to look at an analogy that's very equivalent to electric potential, and that's gravitational fields, something you probably learned in first semester physics. So over here I have a whole bunch of text, and basically it says when lifting a 1 kilogram mass 10 meters, 1 kilogram mass 10 meters, the potential energy, which is, if you remember from first semester, potential energy equals mass times gravity times height, changes by 100 joules, because 1 times 10 times 10 is 100, okay? But for a 5 kilogram mass, it would change by 500 joules, okay? So in this picture, this 5 kilogram mass has 500 joules of potential energy, whereas this 1 kilogram mass has 100 joules of potential energy, okay? Now, if I were to ask you, what is the work per mass, okay, or basically joules per kilogram, we would find out for the 1 kilogram ball, if we would take the do the division here, we would have that it is 100 joules per kilogram of work per mass. Okay. What about for the 5 kilogram ball? And if we take 500 joules divided by 5 kilograms, we would find that it too is 100 joules per kilogram. And you may be saying to yourself, who cares? Well, basically what it's saying is the gravity on Earth isn't different for different mass objects. Okay, the gravity is consistent. It's going to pull the same basically on all objects. Whether you weigh 5 kilograms, 1 kilogram, 3,000 kilograms, it's going to pull on you the same, and basically the potential energy per mass is going to be equal. Okay, and the same is going to actually hold true for basically the potential energy that a charge will have in an electric field. Okay. So that's kind of my analogy, that maybe you can see how gravity gives objects potential energy by moving this mass away from the Earth, and clearly we know if we let go of this ball, it's going to drop down, right, and lose that potential energy and turn it into kinetic energy. The same is true when you take a charge and you put it in an electric field, and you maybe put a positive charge next close to a bunch of other positive charges. That positive charge now has potential energy and is kind of ready to like move away from those positive charges. Okay. So what is electric potential energy? Electric potential energy is usually abbreviated with the symbol U, okay, and it is also in joules, which is abbreviated with J. Okay, those are the units of energy. It's very similar to how in the previous chapter we talked about electric fields and how electric fields could apply a force on an object. If you guys remember, we had an equation, E equals F over little q, okay, and this force was the force that the electric field was basically applying on little q, okay. Electric potential energy looks at basically how much energy a test charge has at a point in space. Okay, so let's say I have like a plate here, and it's got a bunch of positive charges on it, okay, and I take this one little positive charge and I move it close to that plate. Does that positive charge really want to be close to that plate? The answer is no, right? Like charges repel each other. And so by moving this positive charge, say here, it now has gained electric potential. Okay, it now has some energy that basically it may then fly back to this spot over here. Okay. So electric potential, what is it? Is purely location dependent. Okay, just how like those weights were in the beginning of this lesson. Okay, electric potential is the potential energy per charge. Okay, so let's take a look at what that actually means. Potential energy, the units of it are joules, and charge, or Q, is in coulombs. So electric potential is joules per coulomb. Okay, basically, electric potential is used to express the effect of an electric field on a source charge relative to its location within the field. Okay. So here I have a picture of, this is called a Van de Graaff generator, and basically it's got all these positive charges on the outside of the ball, and I bring two objects, okay, near this sphere, both positively charged objects. And an object with 2 units of Q, twice the charge, has a potential energy of 20 joules, okay? And here this one only has 1 unit of Q, or 1 coulomb we'll call it, and it has only 10 units of potential energy. If you take 10 divided by 1, you would get 10, 10, right? If you take 20 divided by 2, you also get 10, and basically what that's saying is they both have the same electric potential. Now, the shame is that in science, there's something called electric potential energy. And electric potential energy is just looking at the amount of energy an object has. So this object here has more energy, it has more joules, but if you look at the joules per coulomb, they are actually equal. But if you just look at joules, this object actually has twice as much energy as, say, this object. So it wasn't me who created it, but basically there's something called electric potential, and there's something called electric potential energy. Anytime you see that word energy, you're looking at just joules. Okay, you're looking at just joules. You don't care about the charge at all. Nothing with coulombs or any of that stuff. It's just energy, which is joules. So what we're really leading towards is starting to talk about how electricity runs in circuits, whether it's through a battery or whether it's from We energy. And basically, electric potential in circuits is what causes or what gives electrons the push in a circuit, okay? And basically how a battery works is it establishes an electric field within the battery, okay, between the two terminals. And this plus here is indicating an area of high, we'll call it potential. Okay, we'll call it high potential. And this negative is an area of low potential. And basically, what this battery does is it does work on the charges that are going through this circuit, this little tiny circuit. And basically what ends up happening is that as a charge leaves this area of high potential, it travels along the circuit, it hits the light bulb, it causes the light bulb to light up, it uses its energy, and then it comes back to the battery to then basically have the battery do work on it and force that charge over here to the area of high potential. Okay, it's kind of like lifting a rock up from the ground, giving it high potential, and then the cycle repeats. Okay, so a battery has an electric field established between the two terminals. The positive test charge moves through the cell from the negative to the positive terminal. Now remember, a positive test charge would not want to go towards the positive terminal. That would involve work to move that positive test charge from this negative terminal over here to this positive one here. Once it's here, it's just natural for it to flow through the circuit. It's like letting go of a rock. You're holding a rock in your arms and you let go of it, it's naturally going to fall to the ground. Okay, it wants to do that. Whereas the rock, as far as I have been around, have never seen a rock just rise up off the surface of the earth. That would be pretty crazy if that started to happen. Okay. So what is the volt? Okay, well, what the heck is this thing? The volt is the standard metric unit of electric potential. Okay, electric potential. So when you see like batteries that are like a 12 volt battery, a 9 volt battery, a 1.5 volt battery, basically that is telling you how much electric potential that battery has. The volt was named in honor of Alessandro Volta. And basically what 1 volt is, and this is what I think is actually really important, is to realize what these units mean. 1 volt is 1 joule per coulomb. Okay, that is what 1 volt equals. 1 volt equals 1 joule per coulomb. Okay, so basically if you have, say, a 9 volt battery, what that's telling you is that that battery will give every coulomb 9 joules of energy. Okay, basically every coulomb you have will get 9 joules of energy. So if I had 2 coulombs, it would then get 18 joules of energy. If I had 3 coulombs, it would get 27 joules of energy from this battery. Okay, so that's what it's basically doing, is it's telling you how much electric potential the battery has, and that's measured in volts. So here's an example problem for you guys. Moving an electron within an electric field would change the blank of the electron. The mass, the amount of charge, or the potential energy of the electron. Which of these would happen by moving an electron through a electric field? And the answer is the potential energy of the electron would be changed. Okay, moving it through an electric field would change its potential energy, and depending on what direction you move the electron, it would either be raising it or lowering it. Okay, it just depends on what direction it's going to or from. The amount of charge on the electron is not changed, and the mass of the electron would not be changed just by moving it through an electric field. So let's take a little deeper look at what a battery actually is. If a 12-volt battery is used in a circuit, then every coulomb of charge would be then gaining 12 joules of potential energy. Similarly, every coulomb of charge loses 12 joules of electric potential energy as it passes through the circuit. Okay, so again, we have an area of high potential here and low potential over here. And so my positive test charge is going to flow this way. It's going to light this light bulb up and use up its energy on the light bulb, and then head back to the battery to then gain more energy and then to continue the circuit again. Okay, so basically as that guy cycles, it's just going to, lose energy to the light bulb, regain energy from the battery, lose energy to the light bulb, regain energy from the battery, and so forth. So here's another example for you guys. If a battery provides high voltage, it can A, do a lot of work over the course of its lifetime, B, do a lot of work on each charge it encounters, C, push a lot of charge through a circuit, or D, last a long time. Well, remember, what is a volt? A volt is basically a look at how many joules per coulomb. Okay, so if I have a 12-volt battery, I would have 12 joules per coulomb. What does that actually mean it's doing? It's able to basically do a lot of work on each charge that it encounters. Okay, so on every coulomb it encounters, it can do 12 joules of work. Whereas if I had, let's say, a 25-volt battery, it would be able to do 25 joules of work for every 1 coulomb that it encounters. So the answer here would be B, do a lot of work on each charge that it encounters. Okay, that takes care of this video. I will see you guys next time.